Okay, so after having a discussion on the kinetic interpretation of temperature, here we're going to continue that discussion and move towards understanding kinetic energy of a gas. Okay, to sum up what we discussed while we were discussing kinetic interpretation of temperature, we had arrived at this equation V square bar, square root of V square bar is equal to known as VRMS, root mean square velocity, and that is equal to square root of 3 RT by M. In this video, I'm going to look at two different things, or help you understand two aspects of kinetic energy. The first is the relationship between VRMS, that is root mean square velocity, and molecular weight of gas. So let us say we have gas 1 and gas 2, two different gases, gas 1 and gas 2, and their molecular weights are, let us say, M1 and M2 and VRMS 1. This is the root mean square velocity of the molecules of gas 1, VRMS 2, the root mean square velocity of molecules of gas 2. And let us say these two gases, both the gases are at the same temperature, T. So for this gas 1, I can get the equation VRMS 1 is equal to square root of 3 RT upon M1 based on this. And for gas 2, I'll get the equation VRMS 2 is equal to square root of 3 RT upon M2. As you would have noticed, T is same, therefore we have T over here. M1 and M2 are different. Therefore, if I take ratio of VRMS 1 by VRMS 2 is equal to, that would be this term divided by this term, and since M1 and M2 are in the denominator, and 3RT or 3RT will get cancelled, M2 and M1 are the denominator, so I'm just saving time by not doing the math part of this. I'll get M2 upon M1. So this is the equation I was looking for. Right. VRMS 1 upon VRMS 2 is equal to square root of M2 upon M1. And if you try to understand this, try to explain this in words, what this would mean is this. The ratio of VRMS of two different gases at the same temperature is inversely proportional to the square root of their molecular weights. This is the ratio of their VRMS, and it is inversely proportional to the square root of their molecular weights. What do you think would be the real life application of this equation, right, or this particular concept? Think about it. What I'll probably do is at the end of the video, right, if this video is not becoming too long, I'll explain to you or give an example of the real life application of this concept of kinetic energy of gas. Right, let's move on to the next concept that I'm going to cover in this video, and that is about kinetic energy of 1 mole of gas and kinetic energy of 1 molecule of a gas. Okay. Now, kinetic energy of anything is given by half mv square. Right? Therefore, if we have 1 mole of gas, kinetic energy would be given by kinetic energy is half. The mass of 1 mole of gas is capital M, which is molecular weight, and V square would be given by V square bar is equal to half M V square. Now V square bar would be 3 RT upon M. This is without the square root sign, so this would be into 3 RT by M. M would get cancelled, so I'd get 3 by 2 RT, and thus I get the equation that the average kinetic energy of a mole of a gas is equal to 3 by 2 RT. One of the most common equations that you will come across in while we study kinetic theory of gases. Right? So next, we have talked about 1 mole of a gas. Now, in 1 mole of gas, the number of molecules is N, which is 6.02 into 10 raised to 23, Avogadro's number. So if you want to find out average kinetic energy of a molecule of a gas would be 3 by 2 R by N T. I hope you got this. This is the kinetic energy of 1 mole of a gas. If you want to find out kinetic energy of 1 molecule of a gas, divide this by number of molecules, and that is N. So 3 by 2 R N upon 2. And this particular term, R upon N, is equal to, a value of R is known, 8.31 joule per mole per Kelvin. This is 6.02 into 10 raised to 23, no unit because it's number. If I do this calculation, I'll get 1.38 into 10 raised to minus 23 joule per mole per Kelvin. And this constant is denoted by a small letter k, is known as Boltzmann's constant. So if I rewrite this equation, average kinetic energy of a molecule of a gas is equal to 3 by 2, this is 3 by 2 kT, where k is known as the Boltzmann's constant. Right? So with this I have got two equations for kinetic energy, one of 1 mole of gas, the other of 1 molecule of gas. The important thing to notice in these two equations is that kinetic energy of a mole or a molecule depends only upon temperature. R and K are constants. So kinetic energy of a gas is dependent only on temperature. That means it does not depend upon pressure of the gas, it does not depend upon the volume of the gas, it does not depend upon mass of gas. Only temperature defines kinetic energy of gas. And that means if we have two gases at the same temperature, they would have the same average kinetic energy. Average kinetic energy of mole of gas would be same. That's the conclusion that we draw from these two equations. Okay, to end the video, I'll go back to this. We talked about the real life application. I'll share with you one real life application, and the real life application of this is, I'll use the same color over here, is separation of gases. So let us say we have two gases, M1 is 24, M2 is 16 molecular weights, right? 24 grams and let us say 16 grams. And these two gases are in a container. Right? This is one of those gases, and let us say this is the second gas. Now these two are mixed up, and I want to separate them. So what I can do is, of course this container is porous, so it has got small pores on it. And what I would do is that I'll put this in a container, probably connect it to a evacuation pump and evacuate this. The moment we have vacuum inside this, the pressure inside becomes larger, and these gases have a tendency to come out. What is observed is the one which has got less molecular weight, that means this one, 16 gram, that gas comes out of these pores earlier or faster as compared to 24 grams. And the reason is because the one which has got less molecular weight, M2, has got higher VRMS, inversely proportional. So the one which has got lesser molecular weight, those molecules will be moving faster inside this, and therefore they will have a tendency to come out of this faster as compared to the molecules of gas with the molecular weight M1. So this property is used in this particular way to separate two gases having different molecular weights. So that's the real life application of this equation. Thank you.